to get my tablet. I don't have it with me at the moment. All right, so here we have consider solutions of the vibrating string problem. D squared y dt squared equals c squared times d squared y dx squared. And I did talk a little bit about this in class, I think. Do you remember that?
I wasn't there, and I listened to some of the recordings, but I haven't got through all of it.
Okay. All right. Well, let's go with what we have.
I was there and I remember. I'm still confused.
Okay. All right. So the first thing is to understand what these symbols mean. This is the second derivative of y with respect to t, which means that you consider the x as a constant. And this is the second derivative of y with respect to x, which means you consider the t as a constant. So just thinking about this, if I take the second derivative of this function with respect to t, what do I get? That's the first thing.
Second derivative of that function, you're going to get negative sine squared sine of omega t, depending on what f of x is.
Does it? Does it depend on f of x?
Well, it's not a function of t. So
It's not a function of t. It doesn't depend on f of x at all.
So then f of x is a constant, so we can pull that in front, then it just means
Yes.
it's just negative omega squared sine of omega t.
Okay. So in fact, you could write that in terms of y. Let's see if I can do this.
You're breaking up.
All right, you could write the result in terms of y. You still there?
Yes.
I'll just have to speak slowly and clearly. So this is going to be online session on 11/18. Okay, and then here we have all right, so here let me insert that screen clipping. Okay, we've got that, and we've got to make it bigger, and we've got another screenshot, this one here. Okay. And that works well. And then so we have the solution. So let's see. So let me just write this way. D squared y dt squared is equal to, and what you told me was the well, I'll just use w's instead, minus w squared sine, this is what you told me, I believe, f of x. Okay.
Yep.
Okay. All right. So are we all on the same page here? Do you guys see how that happens? How he got that?
I'm a little confused about why it's w squared.
Well, you have to go back to what the derivative of sine omega t is. What's the derivative of sine omega t with respect to t? That's a calculus issue. Should I go? Actually, if
You're taking two derivatives, Chris.
yes,
So is the derivative of sine cosine?
yes,
Yes.
And then the derivative of cosine is negative sine.
yes.
So, and then we have to do the derivative of wt, which would be w.
Correct.
Yes.
Do that twice. So, because if you do the first derivative, you're going to get w cosine of wt. But then you got to take the second derivative.
Got it. Okay, thank you.
Okay,
I got it.
and you can just, I mean, if you're not sure, you can always do something like this, And here you can see the result. If I change that to a w here, it's going to give me the same result, I think. All right, if I do the t, I mean, you can see I'm just playing with this, but all right. Okay. Okay. All right, so very good. All right, so let's go on to the next part. So now we want the second derivative with respect to x. So I'm going to be lazy here. Copy. And then here we got x. And then what's the second derivative with respect to x?
F double prime x sine omega t.
All right, yeah, in fact, now because you're doing the x, the sine omega t doesn't do anything. So we can take this off. I mean, we can take this off. And then we have, let me just write it this way, because I was, whoops, let me not write it that way. Dx squared, like that. All right. So let's set the. All right. So let me put a c squared here also, because there is a c squared, right? All right. So now these two things have to be equal. So what do you conclude?
Negative w squared is equal to c squared times the second derivative of f of x.
Okay. So here I have the left-hand side. Here I have the right-hand side. And I guess you canceled out something.
Yeah, the sine of omega t.
Sine omega t goes away. And we get this. And actually what I'm going to do is I'm going to put the c on the other side. And so I'm going to get, instead of this, I'm going to go like this, if you don't mind. All right, now, all right, so let's see where we are as far as the problem is concerned. All right, so it says, what equation must f of x obey? We got that. All right, this equation is an eigenvector equation where x is the eigenvector. All right, so write this equation as an eigenvector equation where f of x is the eigenvector. Now remember what an eigenvector equation looks like. Or do you remember what an eigenvector equation looks like?
Yeah, so the eigenvector equation is alpha v equals lambda v, is that right?
Well, it's not alpha v equals lambda v.
Well, matrix or A.
AV or LV. Yes, LV. Yes, okay. So eigenvector equation is LV equals, let me just call it, let's just say some constant. So I'll just say AV, something like that. Okay. All right, now, how can you compare that to, now here it actually tells you in the problem what the vector is. The vector is f. Functions are vectors. Oh, here's an eigenvector equation, right? This one says that f is an eigenvector of d dx. All right, so you have d dx f equals lambda f. And in this case, the eigenvalue is lambda. All right, so what do we have here? We've got this equation here, which I will make bigger. So how do you relate that to eigenvector equation?
So can we say d squared dx squared of f equals lambda squared?
No.
V?
No, because
How about,
so what
go ahead.
yeah, what's your L and what's your A? Well, I mean, we already said from the problem already says that your V is your f of x.
So it's minus w over c squared v, if you will.
Okay.
And d squared is that whole right side over dx?
You can write this as this is the second derivative of f of x. So you can write it this way.
So it would be d squared dx squared v.
Okay, so what's your L and what's your A?
Your L is the left side, and your A is.
L is an operator. L is an operator. A is a number.
Oh, so the left side is yeah.
A is what?
1.
All right. Now remember that V. So we know V is F. So that tells us
So it would be
The operator is the right side, right? D squared over dx.
that's right.
So that's your L.
So L is equal to the operator. Yeah. A is a number.
The other side is a number because it's a.
And then A is equal to the number. So what was A?
Negative W over C squared.
All right, there you go. All right. So that, I mean, all I did was fit that expression into the eigenvector equation format, and that's what I got. So are we on the same page?
I'm square.
I got it.
All right. So let's see. So and it's very similar to this equation, right? Very similar to that. All right. Next one says. So I think we're done with this. Okay. And then I think that from there, it seems to me that from there, you can kind of run with it from there. Once you have the equation, I think you should be able to do part B. Well, let me ask you guys, since you're all here, how would you do part B? So the equation in A has solutions of the form f of x equals sine kx. What are the possible values of k? All right, so so this is part B. I don't know why it's doing that. Part B says f of x. I want that small. Whoops. So what does that tell you?
You pass sine of kx through for what did we call it in our second part for f of x?
Yeah.
As the vector.
Sure. What does that tell you about k?
K is the constant.
Well, k is a constant, yes.
the mega.
Why?
Because up on top it's a mega T, so it wouldn't be.
We're not dealing with t. We're dealing with f of x. With nothing to do with t. T is not in this equation anymore. No t. Question is, does this function satisfy this equation? Well, maybe I should let you think about it.
Or let me think about it. Then you'll get K. You actually take. If sine of kx is f of x,
Yes.
the second derivative in terms of x would be k squared, negative k squared sine of kx.
Yes.
So be negative now.
Maybe you need to write it down.
So k would be this w over c.
Well, what equation do you actually get? when you put in f of x equals sine of kx, what equation do you actually get?
Squared sine of, hold on, let me write it down. K squared sine of kx. You get negative w over c squared sine of kx equals negative k squared sine of kx.
Okay. Now you can certainly cancel the sine of kx.
And the squares, you take square root of both sides. Well, take the negatives go away.
Yes.
Square root, you get k equals w over c.
No, not quite.
The modulus of w over c?
What's the solution to x squared equals 4?
Plus or minus 2. So the modulus, or the plus and negative of the w over c.
Yes, that's right. That's right. But I mean, at this point, it's plugging in stuff. And for part C, it's also plugging in.
And how do we just know that f of x is sine of kx?
That's what they suggest.
But doesn't it?
Well, I tell you why. Because people have recognized this equation. If you take differential equations, you will recognize this equation. So that's true. He pulled it in this problem. He pulled it out of the hat. But
It says show that the equation of A has solutions of the form.
yes. So you're reading too much into it. All you need to do is show that sine of kx is a solution. That's what that means. It doesn't mean derive the solution. It just means show it's a solution. It doesn't mean that those are the only solutions either.
Yeah.
So I think you're reading too much into the problem. I mean, certainly it's quite clear that if you take 2 sine, you can multiply the sine x by 2 and you still get a solution. So those are not the only solutions. Yeah, when answering questions, don't try to do more than it asks for. Sometimes.
Are we saying that the possible values of k are infinite in this situation?
Well, no. Adam said, when you plug f of x in there, you have very definite restrictions on what k can be. If you plug f of x into this equation, there are very definite restrictions on what k. I mean, if you plug sine kx into this equation, there are definite restrictions on what k can be. You can't just put in any old k.
No.
So it's not infinite at all. I mean, the answer for k depends on w, but if you're given an equation with the w, you're very limited as to what the k can be. And this part C is very similar in nature to this. Except it's a different kind of restriction. Instead of restricting the form of the solution, you're saying that the f has to satisfy these two equations. So I think I should let you think about that. But it's really very similar to B. The answer is not quite so similar, but the process is the same. So are we good with that?
Good till Tuesday.
Good till Tuesday. All right, yeah, we can talk more on Tuesday. Now, have you tried any of these problems where they talk about making the matrix M diagonal? I didn't talk about that much last week.
I know Adam and I chatted about it, and
Uh-huh.
I'm not sure if we're exactly right, but I mean, wouldn't just simply reducing that matrix make it a diagonal matrix?
Well, but that's not the same thing as expressing M in some basis as diagonal.
Oh,
That's just saying row equivalence.
Okay, we talked about this earlier because what I read was that when it's not diagonalized, it only has one column vector that's eigenvector.
Yes.
So I was thinking no, that it could not be diagonalized.
Yeah. Well, I think we need to go back to the discussion of diagonalize. I don't know why I'm getting a strong echo. Must be somebody has their mic close to their speaker. But whoever did it, whoever is the offending party, just fixed it. All right, let me.
try me.
Okay. All right. Well, let's see if I can find where he talks about diagonalizing. That's one of the weaknesses, I think, of this chapter, is he doesn't talk very much about what it means to diagonalize a matrix. Oh, here he talks about diagonalized. When can a linear transformation be diagonalized? All right, so let's look at this example and see if we can understand this example. All right, so we've got this matrix, 2 by 2 example. We want to find eigenvectors. So he solves the eigenvalue problem. I think we're familiar with this. Standard procedure. Change this lambda to lambda times identity matrix. Bring it to the left-hand side. Take the determinant. Find out what lambda has to be. 2 values of lambda. Find the 2 eigenvectors. Here's one, and here's the other one. Okay. All right, now, but here he doesn't say, yeah, so this is a problem. He doesn't say why that means it's diagonalized. So let me go back up and see. We have to go back up and see a little bit more of what he says about that. Certainly, let's see. Yeah, it's not, I'm sorry, this discussion is not very good in this book. It's really not.
John, I had to look outside of this book and found some information that told me that because I only had one, the way I understood it is because I only had one eigenvector, and it was a 2 by 2 matrix, that it could not be diagonalized.
Well,
Less than.
No, that is correct. But that is correct. But it's very poor explanation in here why that's true. Well, all right. Here he says what it is. He says, all right. So here's the discussion. Here you've got this. So let's see. It's buried in there. It really needs to be amplified. Here he found this example of a linear transformation. Here's the basis. And then here he shows that 3, 5 is an eigenvector with eigenvalue 1. Here he doesn't derive it, but he shows it. 3, 5 is an eigenvector with eigenvalue 1. And then, let's see. And 1, 2 is also an eigenvector with eigenvalue 2. So in other words, L of V1 equals V1, where V1 is this one. Well, here, let me screenshot it so we can get this here. So here, let me just say something about matrix diagonalization example. And then let me screenshot this. So in this case, then this is the matrix L. Okay, and then we have we may verify, and then here what he has here, this part here. So I'll screenshot that. Now, how did it get so big all of a sudden? Let me make it smaller. Oops, sorry. Okay. All right, so we have that. We also have the other one here, which I'll screenshot that. All right, so we have two things here. We have L of 3, 5 equals 3, 5. And L of 1, 2 equals 2 times 1, 2. So let me just say, so I'm going to say, let V, so why did it get so small? Okay, so let V1 equal 3, 5. How did that happen? And V2 equals 1, 2. So in fact what I have is L of, let's just write it this way, AV1 plus BV2 is going to be equal to, well, you know this, you know the rigmarole. That's the same thing as A times L of V1. Sorry. Plus B times L of V2. And but L of V1 is V1. And L of V2 is 2 times V2. So that's actually equal to A times V1, 1, plus B times V2. Okay. All right. So this is the important thing, that if I take any B to 2B times V2, sorry, 2B. All right, are you with me on this?
Yes.
All right.
Yes.
So the point is that now we should be able to express, so now we're dealing with the basis V1, V2. This is linear combination of A, this is AB, so in the basis V1, V2 basis, this is the vector AB. So I can say it this way. Whoops. So what this is saying is that L operating on the vector AB, but this is the vector in the V1, V2 basis. And that's equal to A2B also in the V1, V2 basis. And I should put this another parentheses here. Okay. So in the V1, V2 basis, this vector is AB. And in the V1, V2 basis, this vector is A2B. So that means that in the V1, V2 basis, L is given by the matrix. By what matrix?
3, 5, 2, 4.
Nope, nope, nope. You want to be looking at these vectors. So in other words, if I look at these vectors, that means that in the V1, V2, let me just copy this. It has nothing to do with the original values. So according to this, what is L of 1, 0? It's 1, 0.
1, 0.
Okay, and then what is L of 0, 1?
0, 2.
0, 2. And a stupid thing is not cooperating. Okay. Okay, here, let me get a 0 here. Okay. All right, so what's the matrix? So think of this as a column vector. The input is 1, 0, output is 1, 0. The column vector input 0, 1, output is 0, 2. What's that matrix?
1, 0, 0,
1,
2.
0, 0, 2.
Yes, that's right. It's 1, 0, 0, 2. I'll just do it this way. That's how you do it in. So it's a square matrix. It's a square diagonal matrix. Okay. So whatever you say is that whenever a matrix has a complete set of eigenvectors, then the matrix the eigenvectors, then the matrix expressed in the basis, in the eigenvector basis, in the basis of, let's say, basis of eigenvectors, is diagonal. And what do I mean by a complete set of eigenvectors? I mean that there's
Lambda equals n.
well, it means that if you have an n-dimensional matrix, you have n eigenvectors.
Right, that's what I meant.
It means that the eigenvectors actually form a basis. So I'll just say complete means that a n by n matrix has n linearly independent eigenvectors. All right, so whenever you have as many eigenvectors as you have columns, then those eigenvectors form a basis. And the matrix expressed in that basis is diagonal. So that's the deal about diagonalization. So when they're asking about can a matrix be diagonalized, they're just asking, well, are there enough eigenvectors?
So in number 6, the answer is no. There are not.
There's that. Well, in number 6 or number 2? The one you.
Sorry. Number 2.
Yeah.
Yes. Yes. In number 2, the answer is no. There are not, because there aren't enough eigenvectors.
I mentioned number 6 because I know that's where kind of headed because the question on number 6 we were stumped on.
Well, that's another one you're stumped on?
Yes, sir.
All right. Projection is a non-zero linear operator P such that P squared equals P. All right. First of all, can you think of an example of a projection? A very simple example of a projection.
Well, if P is equal to 1,
Yeah?
for example,
Yeah, sure. That's it. That's a one-dimensional operator. How about a two-dimensional? I mean, you remember that linear operator is the same as matrix is example of linear operator. So can you think of a two by two example?
the
1, 0, 0, 1.
1.
0, 0, 0, 1. 1, 0, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1.
Well, that actually doesn't work, because if you take, if you,
Zero matrix.
oh, well, that's not a non-zero operator. That's a zero operator. So zero matrix doesn't work. That's why I put this in here. So is there something that's not the identity matrix and not the zero matrix that works? And the answer is there is. And I think that finding an example is kind of the key to this problem. So that's what I would recommend you think about this problem. Find a 2 by 2 matrix.
Got it.
Okay, so what'd you get?
0, -1, -1, 0.
All right, now if you do that, so let me just write it here. So you wrote 0, -1, and then you have -1, 0. Okay, so you're saying that p squared equals, all right, actually I think maybe that does work, but let's try it. So you're multiplying that by itself. Maybe that does work. That's kind of strange. Okay, well, that's fine. All right, so if you multiply those two together, you get p squared is going to be what? I wrote the two matrices. I wrote the two matrices there. So let's say that's p is equal to.
Yeah, but you don't get p.
You don't get p. You get the identity matrix.
0, 0, 1. You get the identity.
Yeah, that's not going to work. You get the identity matrix, not p. So that p squared is equal to, whoops, p squared is equal to I. So this is not a projection. Okay, good try.
Okay. That's all I got.
All right, well, but you need to think about, all right, so you can think of an example. So okay, so that's your brain teaser. Now remember that a one-dimensional projection was one. Let's say besides the identity. Okay. All right, but we can actually go on here. Well, you can actually, even you can't think of one, you can still go on. Let V be an eigenvector with eigenvalue lambda for projection P. What are all the possible values of lambda? You can still answer that even you can't think of a P. What does it mean that V is an eigenvector with eigenvalue lambda?
P times V equals lambda times V.
Okay, suppose, PV is equal to lambda V. Let's see if this works.
Can we also say that p squared V equals lambda V?
Well, not quite. Let me just write it that way. So then, all right, but that's a good idea. What is p squared equal to then? What is p squared V is equal to then?
P squared V is equal to PV or lambda.
Okay, that's true. Okay, that's true. So that's equal to lambda V. So you're using this by the projection property.
Yes.
Now, but you can actually find p squared V in another way.
Can you just do P times PV?
Yeah.
P.
Yeah. You can also just take P times this equation. And what does that tell you? What is that going to give you?
P squared V equals V lambda V.
Okay, P squared V. Yes, you can. Yes, that's right. You can take the lambda outside. Okay, so all right. Now, can you simplify that?
Lambda V.
Yeah, that's right. Because PV is lambda V, so that's lambda squared. Okay. So what do you conclude? I mean, the game of mathematics is seeing what's equal. Substitute and see
P
what's...
squared equals, lambda squared V.
Yeah, so this one says P squared equals lambda squared V.
Lambda equals lambda squared.
And this one says P squared V equals lambda V. Yeah. So put them together.
Yeah.
So I said lambda squared is equal to lambda.
Yes.
I subtracted lambda from each side, factored out a lambda, and I came up with my lambda values in 0 and 1.
Okay, that's correct. That is correct. That is absolutely correct.
What I do not know how to do is to show that every projection P has at least one non-zero eigenvector.
Okay. All right, so an eigenvector of P would set, oh, so part C. Okay. Okay, so, okay, part C is asking,
If we use P to the n, do we show that every projection of no, because it's P squared to P, right?
okay, so what about the eigenvector? So we know that, so show that P has a non-zero eigenvector. All right, now we know, one thing that we know is PV, P squared V equals P. That's what we know. We also know that P is a non-zero, matrix, or it's a non-zero operator. So that means there must exist some vector, V, such that PV is not zero. There must exist some vector V such that PV is not zero.
And how do we know that?
Because otherwise P would be a zero operator.
That if P is 0, then PV would be 0.
But that's not what I'm saying. Suppose AX is, suppose I don't know what A is. Okay? But I tell you that for some value of X, AX is not zero. What does that tell you about A?
A is not zero.
And that means A is not zero. Right? So if you've got a non-zero operator, if there's some vector, I mean, if P is non-zero, there has to be some vector that P gives you something other than zero. All right, you think about it. It's true that P times 0 is 0, but that's beside the point. That's beside the point. All right, so the point now is find some, use this V to find an eigenvector. And I mean, what the information you have is basically this here. So I think I should leave you with that. Are we still connected?
Yes.
Okay, yeah, because when the sound goes off, I'm not sure. All right, but so I'll use that as your hint. Use this V to find an eigenvector of P.
Okay, that gives me something to think about.
Yeah, I think you can think about that.
Anybody else have anything?
I'm good.
All right.
Me too.
All right, so we'll meet on Tuesday. We can mop up any questions you have on this, and then let's see, what's the next chapter? I'll probably talk some about the next chapter. Diagonalization. All right, so here it's good to here is what he really gets into, that diagonalized thing. So this is saying what I said before. So yeah, so this will be good. So I'll talk a little bit about that.
Chapter is counting from 1 to 10.
Is it from 1 to 10? Let's see.
No, it was a joke, because counting to 1 to 10 would be easy.
Okay. I mean, how many sections does this have? Let's see.
No idea.
Let's see, 13. The chapters towards the end are not very long. Yeah, actually it's only 4 sections. And then this one, orthonormal bases, that's good. So I may actually do two chapters, orthonormal, because orthonormal is good. Grimm-Schmidt is good. So I'll figure.
I know it's a couple weeks away, but for our final or second test, whatever you're calling it,
Uh-huh.
are you doing it like an in-class test, or are you doing like you did previously with that online?
Well, it's certainly not going to be a open collaboration test. I have to have one test where you work on your own. I have to think about what I'm going to do. I think what I may do is look at these practice tests and see if I can do something off of that. Because he has several practice midterm tests.
Will it be cumulative, or will it just be over the second half of the?
Well, at least mostly second half, but of course there's always some parts of the first half that intrude, because the linear algebra is, the second half builds on the first half, but the focus will be mostly on the second half. I mean, if you think about what we talked about in the first half, how come I can't? Oh, here it is. If you think about what we talked in the first half, system of linear equations, vector spaces, linear transformation matrices. I mean, this is all stuff that we're still talking about. You really can't get away from the first half when you do the second half. I mean, we're still doing row reductions, right? And we're still using systems of linear equations. So that's kind of I can't avoid talking about the first half.
Mathematics is always cumulative.
Well, sometimes more than other times, but this is a case certainly where it's very, very cumulative, and you can't. It's just all very interrelated. Especially the way they presented this book, in that they kind of dangle hints in front of you, and then they flesh it out later. But we'll be good, so I think we'll probably try to get up to this one here. I'm not even sure what least squares and singular values means.
Least squares has to do with linear regression, doesn't it?
Yeah, it does have to do with linear regression. Yeah, so I think I'll probably, it's a nice topic, because in fact least squares is just a linear algebra thing. It's a nice application. It's a very good application. But probably not going to get into this. And I'll have to do that in another class. But I would like to get into this one here. So we'll probably do. So I mean, basically, there's after Thanksgiving, there's basically 2 weeks, sort of. I mean, 1 week sort of for review. So we can count on covering these three. Well, let's see. It's actually going to be 4 sections here. But I think these are relatively short sections. Like this one should just be a few pages, I think. Let's see, does this go out more? Yeah, see, this is very short section here. And this one here, this one also a very short section. Alright, this one, I may or may not do all of this. Well, this one is very computational. I probably will try to do all of this, but it's very computational, so I think it's not a very highfalutin theory. All right. Well, let me stop this recording.